I hope you all are doing fine. We'll first go towards introduction to our problem. Many industrial applications, such as steam generation in a boiler or air cooling in the coil of an air conditioner, can be modeled as two-dimensional periodic heat flow. This tutorial illustrates how to set up and solve a periodic heat transfer problem given a pre-generated mesh. The system that is modeled is a bank of tubes containing a flowing fluid at one temperature that is immersed in a second fluid in cross flow at a different temperature. Both fluids are water, and the flow is classified as laminar and steady, with a Reynolds number of approximately 100. The mass flow rate of the cross flow is known, and the model is used to predict the flow and temperature that result from convective heat transfer. Due to symmetry of the tube bank and the periodicity of the flow inherent in the tube bank geometry, only a portion of the geometry will be modeled in ANSYS Fluent with symmetry applied to the boundary conditions. The resulting mesh consists of a periodic module with symmetry. In this tutorial, the inlet boundary will be redefined as a periodic zone and the outflow boundary defined as its shadow. This tutorial will demonstrate how to do the following: create a periodic zone, define a specified periodic mass flow rate, model periodic heat transfer with specified temperature boundary conditions, calculate a solution using the pressure-based solver, plot temperature profiles on specified isosurfaces. The problem is shown in the figure, which is described as: this problem considers a 2D section of a tube bank. A schematic of the problem is shown in the figure. The bank consists of uniformly spaced tubes with a diameter of 1 centimeter, which are staggered across the cross fluid flow. Their centers are separated by a distance of 2 centimeters in the x direction and 1 centimeter in the y direction. The bank has a depth of 1 meter. Here, the temperatures and all the properties of the liquids are given, along with the dimensions of the tubes, walls, and the complete geometry. Now we will go to SolidWorks, create a part, go to front plane and draw a rectangle. We'll give the rectangle dimensions 40 millimeter by 10 millimeters. Now we will draw circles opposite to one another, as you can see, and we'll make these both circles equal and give them dimensions. We'll give them dimensions of 10 millimeter each and give them a distance of 10 millimeter from the edges. We'll repeat the same for the other circle. Now we'll trim and create a planar surface from the sketch. Now we'll save this profile and go to ANSYS workbench. Drag the ANSYS Fluent and import the geometry that we just made. I will go to mesh, wait till it gets open. We'll go to properties of mesh and set the element size to be 0.5 millimeters and generate the mesh. You can see that a mesh is generated. Now we'll go to inflation. Inflation is used to capture the actual flow at the boundary layers. We'll go to geometry and select the two edges that are boundaries of the circle. Select the number of layers, make them 15. It will make 15 layers adjacent to the boundary and growth rate to be 1.05. Now we'll mesh again and we see that it has created mesh adjacent to boundary to accurately capture the flow. Now we'll set the element size to 0.25 and run the mesh again. Now you can see that a fine mesh is generated. Now we will create the name selections. Left side is the inlet of the fluid, so we will name it as inlet. And right side is the outlet. We'll name this selection as tube top and name this selection as tube bottom. Now we will name the upper surface as symmetry 1, symmetry 2, symmetry 3, and symmetry 4 respectively. Now we have created all the name selections. Now we will update the mesh and close it. I will go to solution setup, set the solver processes to 2 and double precision method and open the Fluent. Select the pressure based solver that's already selected and study fluid conditions. Now we will check the mesh. After the mesh checking has been done, we'll type mesh slash modify hyphen zone slash make hyphen periodic and enter. Now it is giving us the periodic zone. I will go to boundary conditions, go to inlet and check its ID number. We will type 5, click enter. Now it's asking about shadow zone. We will type 6 because it's the outlet. And rotational periodic no. Create periodic zones yes. And it will create a translational periodic zone. Now that the periodic zones have been created, we'll go towards operating conditions and specify mass flow rate. Since the flow direction is x and the fluid is flowing in the one direction, we will set the mass flow rate to be 0.05 and click OK. I will go to energy based solver and set the bulk temperature to 300 Kelvin. Go towards viscous model. We'll select the model to be laminar since the fluid is laminar. I'll go towards materials and import the material water into Fluent database. We'll copy it and create it, the model. We'll go to cells and conditions and periodic flow, heat transfer. We'll select the fluid to be water liquid and apply it and close. Go towards boundary conditions, go towards tube bottom, select thermal, and since the fluid flowing in the tubes has a higher temperature, we will set the temperature to 400 Kelvin in both the tubes bottom and top. Now again we will do the same for the top and set the temperature to 400 Kelvin and apply it. I'll go to inlet, select the periodic and go to translational, click OK. Because it's already selected, go to methods and select the simple model, go to controls and set the energy to 0.6, and all the other properties are already defined. We'll go towards initialization and initialize the solution. Set the number of iterations to 500 and calculate. Now the solution is reversed, so we will go to 500 more iterations and run the solution again. The solution is again diverging, so we will go to 500 more iterations and it has been solved at 1163 iterations. We'll go towards contours, save and display the pressure control. You can see the static pressure control in the window right now. We unclick the global range, go to color map and reduce the color map size to actually and click float to actually visualize what's happening. We'll go to controls again. We'll select all the four symmetries and apply it. Now you can see that it's showing the complete geometry and symmetry. It's assuming that the fluid that's going outward from one side is coming inside from the other side of the heat exchanger. Now we'll go to viscosity, velocity and display its contour and contour for pressure as well. And click the bandit key to actually visualize the complete behavior of the fluid inside the our domain. We'll go to plots and XY plots. We'll create four isosurfaces at different distances. X is equal to 0.01 meter and create isosurface. I will create two other isosurfaces at different distances. Isosurfaces are actually the lines along the XY plane. Select it to 0.2, ISO values to 0.02, 0.2 as well, and create. We will select all three surfaces and select temperature on the y-axis and plot it. Now it's the plot of static temperature on the y-axis and position of isosurface. I will close it, go to contours again, save and display the contours. It's the contour for temperature. Because hot fluid is flowing through the tubes, it's showing red color there because the temperature is high there. Now it's the contours for the isosurfaces that we made. Now we'll close it, go to vectors and plot the velocity vectors. We will select the scale. Scale will reduce the size of the arrows and skip will remove the excess vectors. Select the skip size to 15. As we increase the skip size, the number of vectors is decreasing to visualize the actual behavior. Now we'll reduce the scale of the vector to 0.05. We're reducing the vector size accordingly. Now we'll display it, and it's showing the actual behavior of the fluid inside our symmetrical domain.